Okay, so today I am going to experiment a little bit with trying to optimize some YT operations. Um, this week I've been thinking a lot about some particular areas, and I think until I'm able to actually codify where the slowdowns are, and I do this every so often, um, but until I'm able to actually get that really nailed down, we're not going to be able to make a lot of progress. And I think I know where it is, but I want to make sure. So um, you'll know. So the first thing we need to do is we actually need to get a big enough data set. So I've been looking at the data sets that I have on my machine, and what I came up against was, you know what, I've got this one right here. It's reasonably large. It's data 150. So I'm going to run big proj, and here you'll see I'm executing this script. Here, let me rotate this. I'm executing this script, which runs YT with parallel profile, and it outputs it to this. So this means if we run it in parallel, each processor will toss it out, and the final file name has the excuse me. The final file name will uh, have the task number in case even if you're not running in parallel, as well as the total number of tasks. So I'm going to run this. We'll run it with time just so that we can see what it is. It's not as big of a data set as I had kind of thought it might be. I think that it just has a ton of fields. You see it's only about 512 cubed cells total. I actually output that up here, kind of in an ugly way. And I have it outputted as 14 levels of refinement. I have it toss it through the integration, and then it spits it back out. So if we take a look at this, total of 30 seconds start to finish. And actually just sort of unscientifically, most of that was inside the projection. So let's see if I've still got PyProf to install, PyProf to HTML installed. I actually can't remember. And it might not even work with Python 3, but I guess we'll see. Let's see if this works. Yeah, it does. All right, it's in. So this is the final output. If we look at cumulative time, you'll see almost everything is inside handled chunk. 16 seconds, in fact. If we look at the total time, most of it is in this add chunk to tree method. We will dig deeper into that in a little bit. What I think most, well, why don't we take a look at that before I start saying that it's not the actual source. The other odd thing here is, well, we'll see it when we take a look at this. So let's see, it's all inside data objects, construction, data containers. Make sure I'm mostly up to date. Oh. Yeah, mostly up to date, not totally. But that was a recent fork, so as soon as this is done building, I'll go back to that. We'll take a look at handled chunk first so that we can walk through exactly where everything is happening. So what happens, what goes on, is when we're doing a projection, we save the field parameter state, and then we iterate over each one of the chunks, each one of which we don't do any preloading or anything. We only get our local fields, and we do chunking based on I/O. So the number of chunks inside something like this is going to be, in this case, equal to the number of grid files. So if we look here, see, this is 150. There are 128 of these. So this should get called 128 times. You see that it does. So let's take a look at what happens inside handle chunk. Inside handle chunk, and you'll note that the total time inside it isn't that big. It's only 3/4 of a second out of a total of 16 and 2/3 seconds. So if we look at this, there are probably a couple things that are going on here that we need to think about. Some of them are going to be implicit, some of them are going to be explicit. So the first thing that I want to point out is we do chunk.ires. Now it's entirely possible that this chunk.ires is where a ton of time is being spent. And we're going to find out what that is. So we're going to do, we're going to add another function in here just so that we can, we'll do get ires self chunk, chunk.ires. We'll return it. But here we'll do self.getIres on chunk. Now let's rerun it. Oh yeah, I'm downloading one of Britain's data sets here. But, let me rename this. We'll rerun our big projection script. Now I've isolated all of the chunk stuff into the chunk ires stuff. This should help to draw out what's happening as a result of something implicit and what's happening as a result of something explicit. So when we take a chunk and we call ires or I-coordinates, what we're doing is we're getting integer resolution or integer coordinates. Now there's also f-width, which is the floating point corollary to that, as well as f-chord, which is the floating point coordinates. Okay, so now we look inside here. Let's sort it based on cumulative time. Oh, wow. I guess ires doesn't actually take that much time. Fascinating. It must already be set up at that point. Okay. So that question is answered. That's not where the time is spent inside it. So let's see. Here's allocating an empty one. Here's some multiplication. This is getting chunk ires. And here's add chunk to tree. So let's check. If we look at our cumulative time, add chunk to tree takes up 6 seconds. Handle chunk takes up much less. Where in here do we... chunk wait field. So it looks to me like the biggest issue here is in handle chunk calling get data. And so let's see if we can slice this down a little bit more. Get data inside a data selection object gets called 385 times. Let's see. You can see why it would be called 256. Well, no, it shouldn't. I don't know why it's being called that many times, but we'll figure that out in a moment. And the next thing that happens is the add chunk. So add chunk all happens inside Cython. We aren't going to dig into that just yet. Let's take a look here at our chunking and calling get data on our selection data container. So every time we've got a chunk, it computes the index, it computes the path element. Oh, this gets called. So it gets called to compute the path element as well. So let's simplify this a little bit. Instead of doing integrate, let's do sum. Let's do sum. That'll cut down on one item, which is this computation of the path length. Okay. Let's see how it's going. All right, it finished. So now let's see, index all. This should cut down on the number of get data calls by a fair bit. And this will help us draw out some of the things that get called repeatedly or that store a lot of memory that we don't need. So you'll see now get data and construction data containers is called only once. Selection objects get data is called 257 times. That's great. So that means it's getting called twice per chunk. So let's see if we can figure out where that is. Our weight field is none, so it shouldn't be in there. But we've got our chunk field here. I suspect. Well, let's take a look. So now we're going to try a different method of looking at this. We're going to use SnakeViz. SnakeViz is pretty cool. I don't have the easiest time using it for my initial pass at some data. But here we're going to see if we can dig in. I specifically want to find get data inside selection data containers. So let's see, get data. Oh, search. And now if I click on this, it should. Do I have to double click? Let's see. Data selection objects, get data. Yeah, here it is. Get base chunk and read fluid fields. So there are a couple things here that we need to note. First is that identify base chunk gets called a fair bit, and it does count selection. And then, there's no way that sum actually takes up that much time. It's probably because it's all inside this count and get selector mask. So about half of the time that we spend reading from grids, we do getting a selector mask. Now that gets reused over here, I believe, but the cost of reuse is pretty high in that it stores the data in between them. Okay. So this brings us back to the most expensive part. Let's take a look at grid geometry handler. So this is where everything costs the most. What we end up doing is we call select grids. That figures out which grids overlap with our individual data selectors. And then the more expensive part is, for each one of those grids, we then figure out how many zones it has so that we can pre-allocate. Let's take a look at the awk geometry handler. Oh, I guess we don't have that. So let's do ArtIO data structures. ArtIO has this identify-based chunk. And what it does is it sets up a, you'll note that here this current chunk count selection, it sets YT data chunk to have that size. You'll hear this one, the size is equal to none. So let's try emulating that here. Instead of doing any counting, everywhere it says that we want something, yeah, I'm going to make backup lines here because I don't want to deal with all the Git stuff. So this will probably error, but let's take a look. Maybe it's actually taking a lot longer now. There's also the possibility that when I did that, it simply put it into a unfinishable loop. But this once again is demonstrating to me that oh no, it did it. Yeah, this time it took a lot longer. Let's see how the time is distributed this time. Yeah, it spends a lot more time there. Okay. So I guess, here, let me rerun this. What I'm running into now is I know that there's a way to speed this up. What I want to do is I want to figure out exactly what the root cause is of this slowdown. And I think we can do that. But doing it correctly is a little bit harder than I thought. And remember over here we had identified based chunk. Yeah. This get selector mask and then fill mask regular grid. What? Oh boy, that's not good. All right, let's dig into get selector mask, but first let's reload this. So get selector mask. This does do some caching, which is good. Necessary even. If we didn't cache, it would be a fair bit slower. So if cache mask, let's ignore that part, fill mask regular grid. So let's go to selection routines, fill mask regular grid. It's in base selection object. Selector object. Fill mask regular grid. Ensure code. This is where we do get some slowdown from this. So we've got our profile results here. I'm going to comment this out. See how much time is actually spent inside our units conversion. I don't think this will take too much time. Now, let's, this is our old one. Let's take a look at our new one. And in general, these should be, the disk is pretty hot at this point, so it shouldn't be too bad. Oh, and actually I should probably be doing this with one so that it's not actually hitting the disk at all. Okay. Huh. Weirdly, it took a little bit more time. Okay. Let's go back here. We'll do the sum of ones. Now let's take a shot again, this time without any disk I/O. Once again, it's in handled chunk, index. That's not the one that we want. I coordinates. Just probably just calling the fill mask. All right, another trick we can do is we can look at our function caller table. And let's see everything that is called by handle chunk. So we get about 6 seconds added from add chunk to tree. We will take a look at that. Oh. 2 seconds on check derived fields. Yeah, I knew that was a problem. Gotta fix it. Okay, 3.5 seconds on our get data, line 606. Oh, that's just the, yeah. iRes takes half a second, 4/10 of a second. iChords takes a long time. iChords might take a long time because it's generating stuff for the very first time. So okay. Let's take a look at the annotated source. Okay. Why do we get no GIL here? Oh, because select grid is no GIL. Fill mesh mask is slow. We're not doing that. Fill mask regular grid. This only happens once per grid. Once per grid. But that is an expensive allocation. Why is this slow? Ref nanny, get buffer, validate. Safe release buffer. Which buffer? Child mask. Alright, let's take a look. In general, I'm not a huge fan of just doing Cython stuff, but let's take a look here. I'd rather algorithmic fixes, which is where a lot of them are, which is the best place, but to do this stuff, but maybe... I know there's one for initialization check. There we go. All right, let's try something. This is not a panacea. But it might help a little bit. And then we'll take a look at the annotated source again to see. Whoa, wait, that can't be right. All right, so it is getting this, the ref nanny is still all there. What happens if... Can I compile it still? Nope. Let's see. How many places might I have to change it? Region selector. So right now, let's see if we can use memory views instead. Those might be a little bit faster. And I'm also going to re-annotate, and let's see what the re-annotated version looks like. I'm going to keep my old window open so that I can do direct comparisons. Let's see if we can get rid of some of the ref nanny. Now, I'm probably going down the wrong hole here. This is probably the wrong place to look. I'm starting to... maybe it will do something for us, but we don't call the function that many times. So I'm still kind of skeptical. Now we got to do this in region as well. Oh, that was region. Okay. It's not releasing any buffers or anything like that, so maybe that's... That shouldn't have too much of an impact. That being said, it's worth checking. Only 36 gigs done. Yeah, I doubt it's going to have much of an impact, but it is interesting to think about where and how many micro optimizations it takes to get a macro optimization. But that's the old one. Whoa. Right. This one used I/O. The I/O only added a couple seconds, but fill mask regular grid. Yeah. Almost no reduction in time. And that's, I don't know why I even did that. All right. So let's take a look. You know, the other thing that might do this faster. For a long time, I wanted to do this and move a lot more of the calculation into Cython. One of the reasons that we do this set of calculations right here, and we have to do all this caching and whatnot, is because we call it from within these generator functions. So like get selector mask in many ways gets called just from within some generator functions. And I think that I'm talking myself back into no longer exposing as much of the grid object, and relying on a grid tree for that. Well, Perhaps it's time to try that again. Last time I worked on this was, oh jeez. Why would I do this? All right, it's got to be a different branch. Let's see. Okay, grid visit PR is indeed the one. All right, lot of conflicts. Oh, I just list the conflicted ones. What is porcelain? Huh. Okay. Let's go through this one at a time. All right, here's the median. So here in the old one, we had cdef void visit grid cells. It looks to me like the main difference here is the old version used cached mask equals null because we were allocating it. No, the new version I'm on grid visit, so head is me. Yeah, so go with that. Oh, you know what? We did change all of our Python routines to import things differently, but yeah, this looks like a sorting issue. So I'm going to guess that this is all going to get hit by the allocator, or the, what's it called, the sorter. This one, let's take a look at our grid geometry handler. This is all related to the indexing. Okay. Yeah, I think Clement probably needed to, I don't remember why we did it, why I did it this way, but I will get back to that. Bit array should come first. Selection routines now, and then test container. This is all just sorting. Okay, we merged it. It might throw a fit because of this does take a little bit of time. I'm actually not sure why it's installing all this stuff. I should have environments cached. Ooh, I missed a... We'll add these back. All right. Redefinition of assert equal. Ah, yeah. Same thing. I just added that one though. Okay. Ugh. Fine. So let's add all this stuff, and then maybe I'll be able to commit a merge. And then maybe be able to use this branch. Okay. Now it's entirely possible that lots more is going to be broken here. Now I'm going to show you my notes about this. So I keep notes on a lot of this stuff. June 23rd of last year, I spent some time working on this, and you'll see that it's in the YT 4.2 directory, but that's not going to happen. Let me go ahead and take some more notes here. Today I merged with current upstream. Did this on stream. Alright, so let's go over what my notes previously said. It's hard to remember why the grid data files was mandated when I thought that the indexer was sufficient. If we reduce the number of places that a file name shows up, instead have it redirect it to a grid data file. Oh, I remember thinking that. Part that seems to be operative is this. Replace some of the logic more broadly. If we make the assumption that all of the grids have file names associated, we should be able to generate our grid data file objects uniformly. Moving the file name and data file creation and grid geometry handler seems possible. Then we still need to get that information into the grid tree object. Not sure I believe that anymore. But what usually happens is I think that I don't and then come back to it eventually. So. And we're at 46 minutes. I think I'm actually going to call it here for the day. I'll probably continue with this another time. Yeah, thanks for joining me. Have a safe weekend. See ya.